Hey everyone, we're going to start into chapter 2 in this video. This chapter aims at a very important part of chemistry, acid-base chemistry. So you have talked about and learned about acid-base chemistry in the past. This is one subject that seems to sometimes challenge students, and so we kind of hit on it over and over again. So we're going to learn about it and remind ourselves about some acid-base chemistry in this chapter, and then we are going to see acid-base chemistry in many different times throughout this course. So when we run into a step in a reaction that involves acid-base chemistry later, if we can recognize it as such, and if we're comfortable with that, then we can just say, oh, that's acid-base chemistry. We know how to do that. And it's not like really learning anything new. So we're going to start out by just looking at one of the most common and useful definitions for us is the Bronsted-Lowry definition of acids and bases. We're then going to look at some various examples of these reactions and then talk about some of the relationships between acid and base strength. In the upcoming videos, we'll talk about how structure affects acid and base strength. We will then, based upon that, be able to predict the direction or the outcomes of reactions, whether if we mix an acid and base, whether that equilibrium will lie toward the product side or lie towards the reactant side. We'll then look at how changes in pH can affect the structure of acids and bases. It has a lot of practical application in the organic lab, and we'll finish off by an additional definition of acids and bases. So the most commonly applied definition of acids and bases are the Bronsted-Lowry definition. Okay, so in this case, if you remember back, an acid is going to be a proton donor. Remember, a proton is just an H+, and a base is going to be a proton acceptor. All right, so it's all about the transfer of protons. So here's an example down here at the bottom. Some of these things we should recognize all of these from Gen Chem. So we have this acid, we have hydrochloric acid. Right, and we have OH minus, what's that? So that's hydroxide. Right, and that's yielding water, chloride ions. All right, so we can take a look at this reaction, and what we might notice is that the proton that's being transferred is this one on the hydrochloric acid. It gets transferred to hydroxide to generate the water. All right, so in this reaction we have several different components. We know that hydrochloric acid is, sorry about that, I didn't want to do that, is the acid. Hydroxide is playing the role of the base. So what's the role of water? What do we call that? Okay, so acid-base reactions are always in equilibrium, which means that this process is dynamic going forward and backward. So we have to have an acid and a base on each side of the reaction. So in this case, water is going to act as the acid on this side. And to designate that it's on the product side, we call this the conjugate acid. All right, and then chloride is going to be the conjugate base. Right? This type of arrows here designate that this is in equilibrium. All right. Let's remind ourselves of some of the relationships that we've already learned about acid-base chemistry. Okay? For all equilibria, we can describe something that's called the equilibrium constant, right? So remember that the equilibrium constant refers to, or is represented by, the concentrations of the products over the concentrations of the reactants, each concentration raised to the power of its stoichiometric coefficient. So these are all ones, so we don't have to worry about that here. So we have the products over the reactants. And remember that for an equilibrium constant, if K equilibrium is greater than 1, what does that mean? Okay, that means that the reactant, the reaction equilibrium lies towards products. Okay. Right? Because the numerator, to be greater than 1, the numerator, which is the products, has to be bigger than the denominator. If the equilibrium constant is less than 1, that means that the denominator is bigger than the numerator, and so that means that the equilibrium lies toward the reactants. All right? We have a specific equilibrium constant that we use for acid-base reactions, and so this is the acid dissociation constant. We call it Ka. All right, and the only difference here is what we've learned we've done before is that because water right here is a pure liquid, we're going to leave that out. So the Ka value for this is going to be hydronium ion concentration times the conjugate base concentration over the concentration of the acid. All right? And this works in just the same way, right? So if we have a very large Ka, right, this is going to equal, this should be a big K, it's going to equal a strong acid, right? And if we have a small Ka, this would be a weak acid. All right, and these numbers can vary from, very large, 10 to the 10th to very small, 10 to the minus 30th, right? So they're a huge range of numbers. All right, so oftentimes what we do is we use a log scale, and so we use what's called the pKa. And so the pKa equals minus the log of Ka. All right, and so the trend that we get here now is that if we have a large pKa, all right, this is going to equal a weak acid, or a weaker acid. And if we have a small or even a negative pKa, these will be for very strong acids. Okay, so these go in inverse relationships. Okay, now the pH, even though it's listed in the same form as the pKa, it's still a log scale, is something, represents something different. Okay, so the pH equals minus the log of the hydrogen ion concentration, right? So if we have a very low pH, remember the solution is acidic. And if we have a high pH, then the solution is basic. Okay, but even though these two have the same type of form, they're fundamentally different. Okay, so the pKa is a property of a specific molecule. Okay, so it's like its boiling point or its melting point. It's a specific property. So it would be a constant, right, for a given molecule. Okay, but the pH is not a property of a molecule, but this is a property of a solution. Okay, and for a pH, it doesn't matter what acid generates or gives off the H plus, right? We could have a hydrochloric acid, and we could have sulfuric acid, and if we adjust their concentrations, we could get the same pH, right? So we can always modify the pH just by changing the concentration of the acid or the base. The pKa, because it's a specific constant for a given acid, doesn't change. All right. All right, so let's look at some examples. All right. So in both of these examples, we notice that we have some compound reacting with water. All right. And in the beginning, it's not always completely obvious in these reactions which species is going to behave as an acid and which one is going to behave as a base. All right, so I'm going to just show you some examples. In the next video, we're going to go through and talk about acid and base strength, and so that will help us to be able to predict these reactions on our own. So the basic rule is that whichever is the stronger acid, that's going to be the one that donates the proton. Okay, so anybody remember what this compound is on the upper left? All right, you remember that structure? We used it quite often as a weak acid in general chemistry. All right, so this is acetic acid. Where does acetic acid come from? Okay, acetic acid is the main component in vinegar. Right, so we've got acetic acid reacting with water. Okay, and so the acid is going to donate. It's going to act as its acid. It's going to donate a proton. So what's going to be the base in this reaction? Okay, so water is going to act as the base. Okay, so water is going to pick up a proton from acetic acid. And we are going to get the conjugate base of acetic acid. Okay, this is called acetate. Plus, what's the other product? Plus a base. If water picks up a proton, it's going to generate hydronium ion. All right, so let's just label the other components. So acetate is going to be the conjugate base, right? Acetic acid gave off its proton, and then generated its conjugate base, and hydronium ion is going to be the conjugate acid. All right. As we go through this class, we're going to commonly use arrows to show how bonds are formed and broken. All right. So I'll just give you a little peek at this. We could describe this by showing a pair of non-bonding. Remember, we know that this oxygen has two pairs of non-bonding electrons. One of those pairs is going to be used to form a bond to the protons. Okay, so these electrons are going to form a bond to this proton, right? And the electrons that are in the hydrogen-oxygen bond, these electrons are going to go back onto the oxygen. So these are going to go over here. Okay, so these types of arrows show the movement of electron pairs. Okay, and if we put in the non-bonding electrons that were already here, we can then fill in the non-bonding electrons over on our product side. So we had 2 pairs of non-bonding electrons already there, and then the electrons in the hydrogen-oxygen bond also went onto that oxygen. So now there's 3 non-bonding pairs, and we have 1 pair left on the oxygen of hydronium ion. Right, so we could go back, we already know, we could go back and calculate formal charges of the oxygens in acetate and hydronium ion and prove to ourselves that those charges are indeed correct. All right, so let's do one more example here. This is called ammonium ion. All right, and again, that's going to react with water. So like we did above, ammonium ion is going to react as an acid. Water is going to react as a base. And this is going to yield ammonia plus hydronium ion. Okay, so again we have the conjugate base and the conjugate acid. All right, if we want to use our arrows to show the movement of the electrons, we'd have a pair of non-bonding electrons on the oxygen. It would form a bond, use those electrons to form a bond with this proton, and those electrons would go back onto the nitrogen. Right, so notice on the reactant side of this reaction, of this equilibrium, we have a net plus charge from the ammonium ion, and if we look at the product side, we still have a net plus charge, but now the plus is on hydronium ion. Okay? All right, let's work through a few more examples. All right, so the top one has acetic acid again, and acetic acid, instead of reacting with water, is now shown as reacting with hydronium ion. Okay, so what's going to be the main difference here? So again, this is acetic acid, and we have hydronium ion. Okay, in the last example we saw acetic acid reacting with water. So what's the difference between water and hydronium ion? All right, well, hydronium ion has an extra proton, and so that makes hydronium ion into a much stronger acid than water is. Okay, so in this case, the roles are going to be reversed. So hydronium ion is the stronger acid, so this is going to act as an acid, and that's going to force acetic acid, even if it doesn't like it, it's going to force acetic acid to act as a base. All right? So we've got to figure out then where the proton from hydronium ion is going to go on acetic acid. So we essentially have 2 possibilities, right? Because we have 2 different oxygens, right? The only place that the proton can be accepted to are on atoms that have electrons that can be used to form the new bond, right? So both of those oxygens have non-bonding electrons that can be used to form a bond to a proton. Okay, so we've got two possibilities. Let's draw those out. We can either protonate on the top carbon, oxygen I mean. Right, so we draw this out. We put a proton up here on the top oxygen. All right, and that would give us a plus charge on that oxygen. Remember, oxygen, when it has 3 bonds, 1 non-bonding pair of electrons, has a plus charge, just like hydronium ion, 3 bonds, and it would have a non-bonding pair. The other possibility here is that the acetic acid gets protonated on the other oxygen. So that would be on this oxygen down here. We'd have a non-bonding pair. That would give us a plus at this position. All right? And then, of course, the other byproduct here, or the other product, would just be water. Okay? So how can we know, how would we predict which of these two products would be the correct conjugate acid? Okay? All right, so what I would say is that in this case, we're going to form whichever one of those conjugate acids is more stable than the other. Okay, so we want to know which is more stable. Okay, and we'll talk about some of the reasoning here later, but so what we want to see, or what we might recognize, we've talked about this a little bit, I think, in general chemistry, is that in the structure on the left, the electrons here can be donated to form a double bond there and push these electrons up onto the other oxygen. All right, if we do that, we form another structure that looks like this. All right, so this has 2 non-bondings up here now. This has 1 less. So where's the plus going to go now? Okay, the plus is going to go down here. All right, so compare those two structures. Okay, what's the difference between these two? Okay, the only difference between these two is the position of the electrons. Okay, and so these are in fact what we'd call resonance structures. Okay, and we could use a double-sided arrow to indicate resonance. Okay, so we got 3 kinds of arrows so far. We have this kind. This is the movement of electron pairs. We have this double arrow, which is equilibrium. And we have this kind of double-headed arrow, and this means resonance. Okay, we'll have a whole chapter later on resonance, but a key thing about resonance is that these two resonance structures, this one and this one, are not really separate structures, but they're showing how the electrons are distributed and how they're shared. And because these electrons are shared, that makes that more stable. Okay, so this one, or actually this pair here, is more stable. So in this reaction, we would protonate up on this oxygen. Okay? Alright, so we'll learn a little bit more about resonance later on. Like I said, there's a whole chapter on it. Alright, so let's just fill out these other reactions. So now we have, this is called an amine, and it's reacting also with hydronium ion. So nitrogen with 3 bonds has a non-bonding pair of electrons. So these electrons can go like this. And if we do that, it's going to give us this ammonium ion plus water. Okay, so the ammonium ion would be the conjugate acid, right? And water would be the conjugate base. All right, we could do the same thing. This is an alcohol down here. Alcohols can react in that way as well. This hydronium ion is a stronger acid than any of these species. So it's forcing all of these other compounds to act as bases. We get this plus water. Okay? And one thing that's interesting about alcohols is they can act as bases, right? This is acting as a base here. And they can also act as acids. Just like water, right, can act as an acid to generate hydroxide, and it can act as a base to generate hydronium ion, right? So in this case, we have it with hydroxide. Hydroxide would pull off this proton to give us O minus like this, plus water. All right, so these are just some examples, and as we learn which acids are stronger than other acids, we'll be able to predict these each time. Okay, so it's always the stronger acid is the one that donates its proton. Okay, so let's just make sure we know. So this is being the acid. This is the base, right? Here's the base. Here's the acid. This is the base. This is the acid. And we have it up here as well. Okay, so these are just some good examples. Alright, so in the next section, what we're going to do is we're going to go through and talk about what it takes to make a strong acid or a weak acid. We're going to look at how the detailed chemical structure influences the strength of the acid.